thanks. I want to talk about different governance things. I'll focus on a recent paper with Alon Benheim, who's at Microsoft, and Jerry Tsoukalis, who's at BU, about quadratic voting. But hopefully at the end, we'll have some time to talk about some of the other stuff on voting that I've been working on. I think there's a ton of really interesting questions about how to model voting behavior in the blockchain space. And as we said, like, it would be great to have questions. So the kind of voting that I'm talking about here is this kind of voting for platform governance. So here's a screenshot of some recent Uniswap votes of should you deploy Uniswap version 3 on the Filecoin virtual machine, or things like this, right? So you can imagine these kind of yes/no votes that people are making. And as I'm sure you know, most on-chain voting is stake-weighted. So your voting power is proportional to your stake. And quadratic voting asks the question, what if your voting power were proportional to the square root of your stake instead of linearly depending on your stake? And so one place where this is done is in Axelar. So Axelar is a cross-chain message passing protocol. It's its own blockchain that's built using the Cosmos SDK, and it's used for passing messages back and forth. And validators can join Axelar to participate in a threshold signature scheme to read messages from one blockchain and sign messages to the recipient chain. And if you look here, it says, so here's some validator. They have, their stake is 52 million, but their voting power, where it says under quadratic, is only 7.2 thousand, which is roughly the square root, right? So Axelar actually is doing this in practice. They only do this for processing their cross-chain transactions. They don't do it as part of their consensus mechanism, but it's still a place where it is being used. And it's been proposed for governance in platforms like Polkadot, where it's been discussed. It's not actually used there. It's been proposed as part of Uniswap governance. It's not used there either, but people are discussing, right? It's an open question of what kind of benefits would this bring? And so this is sort of the idea of some of this research is sort of what can you get from quadratic voting? So one other place where it is used is in crowdfunding. This is going to be a little different from the model we talk about, but I wanted to bring it up because it is a place where quadratic mechanisms are being used. So we have Gitcoin grants here. And the idea of quadratic funding or crowdfunding like this is you have some user I, and they're going to donate some funds towards some particular project. So project P, and they donate this amount V sub I P. And instead of receiving the sum of the VIPs, project P actually receives the sum of the square roots squared. And this again kind of flattens out the donations made by whales. Now, one problem with this kind of crowdfunding that's sort of well known is that this could actually run a deficit, right? The amount of money you take in is the sum of the VIPs, right? That's how much is taken in, but you're giving out a different amount. And these two things may not match. And so in practice, you need some way to fix that discrepancy. And in Gitcoin grants, the deficit is made up by donors, and in this case, mostly the Ethereum Foundation, but it could be any kind of donors. But this is an issue that sort of quadratic crowdfunding faces. But we're not going to be talking about the crowdfunding. We're going to be talking more about the kind of governance like Uniswap governance. Yeah, so the question is, why square root? Okay, so there's a couple of things. So the first intuition is that it should essentially devalue whales, right? So in stake-weighted voting, if I have 100 tokens, my vote counts 100, and I could maybe, I can really influence the election or influence the funding if I have a large fraction of tokens. But if we take the square root of everything, it flattens things out. So now to get an influence of 100, I would have to stake 10,000 tokens. Whereas people who have small weights, right, if you only staked 1 token or you only donated 1 token, whether you take the square root or not is the same, right? And so this is kind of saying it's a way to to downweight the vote of whales, or to make the system sort of less amenable to take over by the people who have the most money or tokens.
Can I ask a question? But you can, why like square root and not like
yeah,
root in the power of 3 or 4?
Yeah, so absolutely, that's a great question. And so for the intuition I just gave, that intuition works whether you take the cube root or the fourth root or whatever. One argument is that square root is sort of the most natural. It's the first, natural number above 1. But actually, the original papers that proposed this from Lally and Weil show that it's actually the power 2 is the exact optimal for optimizing some notion of social welfare. And I'll talk about that a little bit at the end. Their model is kind of different from ours, and so we don't have the same optimality result. But actually, that was sort of one of the motivations for this study, was they show in this very specific model that this quadratic power is optimal. And we show that it's actually not optimal in the model that we consider, which I think is sort of more accurate to the blockchain space. But I'll go through our model first, and at the end, if we have some time, I will quickly go through the Lally and Weil model. Yep, is there a question?
Yeah, quick question. Can you explain, are you going to explain the formulas you have on the slide? Why does the project receive the square of the sums of the...
I mean, so this is how Gitcoin Grants does it. This is how the original crowdfunding papers defined it. You could, in principle, not have the square. You get the square also ends up being it basically renormalizes things back up, right? If you're square rooting everything, you're bringing it down, and you square it and you bring it back up. And this is sort of looks now more like the kind of like a 1/2 norm. But we can talk about this a little bit more at the end when we look at the previous work. Like, this is a little bit of an aside. It's like, this is a model that's different from ours because we're not considering crowdfunding where people are actually putting in exact money. I mean, maybe they're staking in order to be able to make votes, but their stake doesn't go towards a project, right? So in the kind of model that we're thinking of, where you stake to make votes and your votes have some influence, that there is no kind of squaring at the end here, right? This is only in this case where you're actually giving money, and the money you give is going towards a project.
You can also ask another very, very basic, stupid question. Yep. So if I want to have 100 voting power in this system, I could stake 100 individual entities. Each one will take 1 token, and then the square root of each one of them will be 1, and I have 100. Or I could be stupid and try to become a whale and stake 10,000, and then the square root would be 100.
Yeah. So no, that's actually a really important point, and it's a crucial part of basically any quadratic voting system, which is that in quadratic voting, you are incentivized to basically make pseudonyms and split your stake or your influence. And so that's actually, I think the next slide is, in order to do that, you need some kind of identity mechanism. Gitcoin has this idea called Gitcoin Passport. And so in order to participate in these things, you need to identify yourself in some way. They allow different Web 2 kind of identifications. You can identify with a GitHub account or other things. But basically, this is actually a really critical point. And it's not something we address really here, but anytime you're going to deploy a quadratic voting mechanism, you need identity controls. And it's a big obstacle to deploying them. And so for the rest of this talk, we're going to basically assume that there's some external identity control, but the whole system totally breaks down if you can make pseudonymous accounts.
Yeah, that's actually really important. What that means is that the effort for an attacker to take over a percentage of the community is actually square of what a real, honest, diversified community power has.
Yeah.
Okay.
Yeah. So so let me now talk a little bit about the model that we're going to think about. So we're thinking about these kind of binary proposals, like the type of proposals you see in Uniswap or Compound or things like this, where it's a yes/no vote. Should we, should we deploy on some new chain, or should we add some new token to our list of approved collaterals, or something like this? So it's yes/no votes, and you have a whole bunch of voters, and they have some guess about whether they should vote +1 or -1. So this is their signal S1, and they have different utilities if this vote goes through. All right, so the voters, some people may stand to make a lot of money if this goes well, and some of them may make almost nothing. They don't really care. But we're going to focus on this case mostly where there is kind of a correct answer. People may not know what it is, but it's like, if we increase interest rates, that will be good for the protocol. People may not know what interest rate is optimal, but they all sort of stand to benefit if the optimal thing is chosen. And so we're thinking of this more as like a crowdsourcing of information, rather than trying to like sort of separate out between two communities who really want different things. So in this model, everybody then, they get some signal, they cast some vote, and the outcome is you sum up the votes, and if it's positive, you go to +1, and if it's negative, you go to -1. This is this discrete voting. And if people have different preferences, you can say the utility is, for player I, is UI if the outcome of the vote goes the way they want. And I was saying before, we're going to focus mostly on the case where everybody is sort of incentive aligned, but maybe has bad information. And so then the net utility is the sum of these utilities, and we're going to focus on sort of maximizing the net utility. So in the baseline case is sort of one person, one vote. This is kind of a really nice benchmark, is everybody just votes their signal, and you add them up, and there's no scaling of any kind. In the quadratic voting setting, you can say a player can choose how many votes to buy, right? How much to stake or how much money to put in, and it costs them F of V. So if you want to buy V votes to either in the plus direction or the minus direction, it costs you F of V. And we're going to focus on essentially these two cases. But again, there was a question earlier, right? What, maybe you have a different power. I'll focus on these powers, M equals 1 and M equals 2. So M equals 1 is to buy V votes, it costs you V units of dollars, and V equals 2 is, M equals 2 is, it costs you V squared dollars, which is like quadratic voting. But again, that sort of this kind of analysis works for any exponent M. And so we're going to think of this now, the individual's utility is UI times the sort of outcome of the vote. We use the psi for the outcome of the vote minus what they paid to cast their votes. And so the net utility is the sum of this. And if everyone's incentive is aligned, then the utility part at the beginning sums up, and then we have to sum the costs. And now one problem with this model, and that's also come up in sort of the previous works that have done this, is that if you're just looking at net utility here and you make people pay to vote, the more they pay, the sort of worse the net utility is if people just have to pay more. But that's kind of an artifact of the system that's not really reasonable. If you have to pay more to vote, that money should go to something. And so all of the previous works consider some kind of redistribution. And so people pay to vote, and then all of that money is redistributed back. And it turns out that in our work and in all the previous works, it really doesn't matter that much how it's redistributed back, as long as it satisfies a couple of things. That one is its budget balance, so that all of the money that people pay to vote is distributed back. And two is the amount you get doesn't depend on how much you put in. And so then it really can't change your behavior. And so the natural thing to do is you get a 1 over n minus 1 fraction of what everybody else paid. And if you sum this up, you can see that this is sort of a clean redistribution mechanism. This was proposed in the first quadratic voting papers. It's sort of the natural thing. It just sort of give everybody back just divide it as evenly as you can among all the people who voted. And so in this case now, we have the welfare of player I is basically UI times the chance they get their preferred outcome minus the cost of their voting plus this redistribution. So that's the welfare they're going to try to maximize. And so the optimization problem, like the voters' problem, is to maximize their own welfare. So they're going to try to maximize this thing, which is their utility times the probability of kind of the correct outcome minus their cost plus the redistribution. And the nice thing now about the redistribution is that it's basically going to sum out with the costs. When we look at the net welfare, it's just going to effectively go away. And so the cost and the redistribution don't affect the net welfare in any way.
Can I ask a clarification question?
Yep.
So basically, just if I get it right, the FV function, it's going to be that if you want to have a higher voting power, it's more expensive, right?
Yeah. So if you want to cast V votes, it costs you F of V. So if you're thinking of like linear stake weighting, if I want to cast V votes on Uniswap, I have to buy like V uni tokens. But you could say if I want to cast V votes, maybe I have to buy V squared uni tokens, and then F of V would be V squared in that case.
But my question, just because of the redistributions of the voting fees or whatever.
Yep.
So it's going to be in a way that if I put more money, then it's going to then it's going to go back and distribute it among everyone. So I kind of have incentive not to put so much money because it's going to be a public good.
Yes, so potentially that's true. Yeah, so that is a part of it, but you get back from what other people put in as well, right?
Okay.
So, and the key part of having the redistribution not depend on what you put in means that if you are the voter and you're trying to find the maximum VI for this, it actually doesn't depend on this last term, doesn't depend on VI, so you can ignore it. The maximization problem, although the amount of money you get depends on this last term, your maximization problem doesn't, and so you can ignore the redistribution. And so that's why people like this redistribution mechanism.
Sorry, when you say it doesn't depend on, so basically, wouldn't it be the case that if we think about, I do have this whatever money I put in auto redistribute back to me, wouldn't that just be like a discount of the function of the FVI? It's just a different FVI, right?
Yeah, it would be then a different FVI, and then you'd have this kind of complicated relationship. Now, if I want to say, is quadratic voting better or worse? It would, if I pay, right, it's no longer quite quadratic voting anymore, right? It would be some sort of discounted quadratic voting, and the discounting would depend on your redistribution mechanism. And so again, like back to these old, the original papers which say quadratic voting is best, you couldn't actually say quadratic voting is best there because the redistribution sort of makes it so it's not quite quadratic voting, and then you'd have to like undo it. And so this is just a nice clean way of separating. But you're right, you could kind of roll it in, but then it gets much more complicated. And so I mentioned earlier a little bit, but the kind of model that we want to think about is when people have imperfect information. And so here's like an example vote from Compound, where somebody has proposed, they say the collateral factor for the BAT token is currently 65%. Should we change it to 62%, right? And I would argue that very few people have like a really strong sort of horse in the game of what this collateral should be. Maybe there are a couple of BAT speculators who care, but most of the people who are Compound voters, right, want to do something that's going to be best for the protocol. And if you lower the collateral factor a little bit, you may get more borrowing lending activity and generate a little more fees, but you also open yourself up to some liquidation risks, and you have to weigh these things out. And I would argue that nobody knows the exact sort of optimal parameter, you may have some guess, and some people may have more informed guesses than others. And kind of a goal of these compound votes would maybe to sort of crowdsource some of these guesses. So this is the kind of model we want to think about, where people have imperfect information, they're trying to make some decision, and you're trying to use the voting as a method of crowdsourcing. And so then the question is, would you do better crowdsourcing with one person, one vote, like, or one token, one vote, so like linear voting, or with quadratic voting? And I just want to mention before we get into this, I'm really interested in this sort of voting under imperfect information. And I have two other papers that if we have some time at the end, I may talk about a little bit more. One of them, which is looking at direct voting under imperfect information. So here is where you imagine you vote actually for the parameter. So like in this example here, in compound, you can't actually vote on a collateral factor. Somebody proposes a collateral factor, and then all you can do is vote yes, no. And if you want to change it, you vote yes, no. Other platforms consider something where I just vote my collateral. I think the collateral factor should be 67%, and I vote 67. And if you think it should be 63%, you vote 63. And then the platform takes like a stake-weighted average of our votes, and that's the collateral factor, right? That's another way to do voting. We call that direct voting. You can analyze that as well. And the goal is to sort of get us to, again, kind of crowdsource as close to the continuous optimal. But that's like a kind of continuous voting instead of a discrete voting. And so I have a paper on that also with Jerry Tsoukalis, which if we have time, I'll talk about a little bit. Another question is around approval voting. And there we looked at electing committees of block producers, and different systems use approval voting, where you don't get one vote, you can approve of as many different options as you want, and they all get your full vote. And the question is sort of how should you strategically vote in an approval voting setting? But in general, I think this kind of idea of thinking about on-chain governance as a kind of crowdsourcing mechanism, how do you get information from a group of people, is like a really interesting and fruitful place to study.
Can I ask a question?
Yep.
Just to clarify, so for this environment, what I need to think in mind is that none of the agents as kind of
none of the agents is malicious in this model, or like has really different preferences from everybody else.
But more than malicious, you know, because sometimes, for example, with stocks holders, there is the idea that maybe sometimes the big stockholder has more information than the other. So this makes it be less kind of the wisdom of the crowd solution problem. It's more kind of the guy with the more information maybe need to take the decision.
Yeah, so absolutely. So our model does capture that. So we imagine people have different information, and I'll get into our model a little bit in more detail, but everybody will have different precision. So all the voters are going to essentially get a signal about what they think is best, and they're going to have different, essentially like variants on their signal. That's going to be public. Basically it's public who's more informed and who's less informed. So yeah, we're going to try to capture that. And in the previous works too, we've also tried to capture that part of it.
So kind of like, if you have a strong signal, it will incentivize you to put more money to influence the voting. Okay.
Yeah, exactly. Yeah. So this model is basically, again, it's a binary proposal, and we're going to assume, sort of without loss of generality, that we're going to just call the good outcome is like +1. People don't know what the good outcome is, but you know, doing the theory part, we can relabel so that the good one is +1. And so voter I has this probability PI of identifying the good option. So this a priori probability is known, and so this is like the voter's precision here. And so some voters have a high PI, and so they're known to be sort of more informed, and some voters have a low PI, and they're known to be less informed. And all the voters want sort of the good option if they could identify what it was, but they have different utilities. So some of them may gain a lot if the good option is chosen, and some of them may gain only a little bit. Like if you're a power user of the system, or you're a big stakeholder or something, maybe you gain more when the good option is chosen. And if you're a sort of casual user or not really part of it, maybe you gain less if the good option is chosen. And so the sort of optimization problem then is basically we're trying to optimize the probability that the good option is chosen, because that actually is going to maximize the net utility. When everybody's incentives are aligned, maximizing the probability of the good option is the same as maximizing the net utility. And so that's what we're going to be focused on here. And right, the reason this is going to work is so each individual person is going to try to maximize their, so voter I has this decision problem. They have to choose how many votes to buy. This is their welfare. They get the UI times the probability of the good option minus their cost plus the redistribution. If we sum this up over all the VIs, the cost of the votes and the redistribution cancel, because that's what we assumed was this budget balanced redistribution. And then the UIs all come out. And so the maximization problem really is just maximizing this probability. So the main question we want to ask in all of this is what cost function f, and in particular you can think of mind f of x equals x or f of x equals x squared, is going to maximize this probability, assuming that each voter is rational and maximizes their own utility, right? So we as this platform designer get to choose how much it sort of costs to vote, and we want to choose one that's going to maximize the net utility. And so as sort of a warm-up, you can analyze this kind of one person, one vote game where basically everyone is forced to just vote. Like they can't buy extra votes, right? You just get to cast your vote. It's not too hard to see as a basic thing. You get votes that are either plus or minus one, and you get the sort of good option if more than half of the votes are in the correct direction. And this ends up being what's called a Poisson binomial. If everybody had the same precision, it would just be a binomial where everybody has, like, what's the probability that if I cast a bunch of independent votes that all have a probability of P of being, plus one, then that would be a binomial. But now this is a Poisson binomial because everybody has different parameters. So this is sort of the baseline kind of case.
Sorry, I have a question. So when you think about individual signals, or should I think about my signal as what's the probability that I think it is going to be plus one? Then in that case, I vote plus one. As long as it's more than 50%, I vote plus one. Or it should be the case that I have a probability that I actually vote, even if I got a positive signal.
Yeah. So you can think of it as basically you're going to vote plus one if you're you're going to vote. The way we've modeled it here is you get some signal and you're going to essentially vote your signal, and you know that your signal is correct with some probability P. And so your choice is not which way to vote. You're going to vote for the thing that you think is better, right? We're assuming everybody's probability of being correct is bigger than 50%. Otherwise, you flip, right? But everybody's going to vote in the direction they think. Their signal is just telling them which way to vote. But your choice is not which way to vote. Your choice is how much to vote, right? Does that make sense? Like this is your decision problem as a voter is how much sort of stake to buy. So, you're faced with this decision of, should we deploy Uniswap v3 to some new blockchain? And you have in mind that I think this is a good idea. How confident you are about that. And now your decision is how much sort of stake should you put into that decision?
Right. I just want to clarify. So I'm still a little bit confused with the signal. So giving some signal, I will have the probability to vote plus one.
Yeah. So well, I was saying so the signal is plus or minus one, and the good option is essentially like hidden, is either plus or minus one, and you don't know what it is. And so now the PI is the probability that your signal matches the kind of hidden value of plus or minus one. And now if I want to make this simplification that I'm just going to call the good option +1, then I'm going to assume that you basically vote +1 with your probability PI. And so, and that doesn't change, like it just makes the analysis a little bit simpler, but doesn't change the fundamental problem at all. And so here, the question we're kind of asking is which of these mechanisms is better, which cost mechanism is better? And it turns out that in these cases where there's multiple equilibria, we have to define what does better mean. There's may not be a total ordering on these mechanisms, basically, like is linear cost better? So we come up with this sort of a very weak notion of what is better. So we have two mechanisms. You can think of like linear voting versus quadratic voting, and they have two sets of Nash equilibria. And we're going to say that mechanism one is sort of worse if it's missing some better equilibria. Under this thing, there's some extra equilibria you could get by moving to the mechanism two. And the worst mechanism you add by moving to mechanism two is better than the best equilibrium that you had before. So, right, this is just coming about because there's actually not going to be a unique equilibrium for these different mechanisms, and then we have to say which one is better. But this should be, hopefully, this is like a little bit funny to say, but hopefully it should be kind of uncontentious that if you have the equilibriums in this green circle, and you say, actually, I'm going to move to this mechanism, I'm going to move to mechanism two, which it gives me some additional things, and everything that I get, the worst new thing that I get is better than the best old thing that I had, right? Then I should move over, right? That's and then we also need to sort of flip it, which is to say this mechanism one would be worse than mechanism two if by moving from mechanism two to mechanism one, I add things, and the best thing that I add is worse than the worst thing that I had to begin with. So we basically say something is better if moving to it strictly increases things, and it's worse if moving to it strictly makes things worse. And that gives us a partial ordering on these mechanisms. And so with this kind of partial ordering, here's what happens when you have just two voters, sort of as a warm-up, because this is what we can draw in two-dimensional space. It's not really, but the thing that's kind of interesting is if you imagine you have two voters and they have different precisions, P1 and P2. And so this is kind of this question when voters, when there's an informed voter and not an informed voter. And here, to make this plot turns out actually to be like really nice if we make the axes not the two precisions, but essentially the probability. C1 is the probability that voter one gets it right and voter two gets it wrong. And this axis, C2, is the probability that voter two gets it right and voter one gets it wrong. And so as we go here, as we go in this sort of X direction, this is voter one is getting better, basically, and this direction is voter two is getting better. And in this case, we actually see that you don't have a strict an ordering. You can't just say quadratic voting is better. In some parameter regions, quadratic voting is better, and in some parameter regions here, so in the, I guess the red is quadratic voting is better, and in the green, the single choice voting is better. I mean, the linear voting, like linear cost. So m equals 1, the exponent 1 is better. And what we've seen here is these are all we can calculate, in the two voter case, you can actually calculate all the voting equilibria that actually come out. And so here there's multiple equilibria in sort of all these places. And yeah, so just in terms of how this is set up, this is the top one is the equilibrium you get under linear voting, and or the equilibria you get under linear voting, and there's only one equilibrium you can get under quadratic voting. And in some cases, in this case, there's only, in the bottom green one, there's only one equilibrium under both. But the equilibrium here is, this is, linear voting is better because both of these equilibria, UP1 and UP2, are both bigger than UP1, P2. Because P1 and P2 are these probabilities which are less than 1. We can actually, in the 3-voter case, we can actually still categorize. Yep.
Just to see, so if I remember from the model, basically the idea, because everything that you pay for voting, you get back. So basically, the utility is more generated by the voting outcome, right?
Yeah. So that's kind of the goal, is to try to focus on this. The mechanism we're trying to find is the mechanism that sort of makes the chance of getting the right voting outcome highest.
Okay. I see. Yeah. Okay. So basically, the idea is that in some scenarios, when you have a linear voting mechanism, it's going to be more efficient because the informed trader can push the voting to the right direction easily.
Yeah.
While in the quadratic, sometimes it's too expensive for him to do it.
Yeah.
So,
yeah. So this is actually a really good intuition, is that quadratic voting really doesn't play well with the kind of information asymmetries, that if somebody has more information, you want them to sort of dominate the vote. And if it costs them too much, they're not going to do that. And so they'll undervote. So basically the people with too much information kind of undervote in quadratic voting. And we get a similar kind of thing in the 3-voter case. The nice thing is, if you imagine that everybody's signals are independent, then once you have a lot of voters, sort of a central limit theorem kind of kicks in, and it doesn't really matter what you do, as long as, if you have a ton of incentive, voters whose incentives are all aligned, and it doesn't really matter how you aggregate them. Yeah, so this is kind of what we were thinking about here. And again, the kind of intuition that comes out in a lot of these works is this thing that you're saying, which is that basically, if you imagine people have different amounts of information, how do you incentivize them to vote, like the people with more information to vote more, right? And quadratic voting clearly doesn't specifically there's nothing to align it to your information. And that's actually true with, linear voting as well. It also doesn't really align to your information. In previous work, when we considered sort of continuous voting, we actually added some places where you can exert effort to improve your information, and it's still, it doesn't, these mechanisms don't work very well. I did want to talk for a minute about these earlier works on quadratic voting, about sort of where the square comes from. And so in the original works from Lally and Weil, there's no uncertainty. The voters have some utility, and to make things, so their model is very similar to ours. We had this thing where your utility is UI times the event that your outcome is chosen minus your cost. They said, well, this thing is discontinuous, and that's hard. So they said, let's smooth it out. So instead of having like a jump where if your option is not chosen, you get nothing, they wanted to make that a C infinity function. So like imagine just smoothing out. So if your event is almost chosen, you actually get some utility, which is not true in real life maybe, but it makes the mathematics much easier. And so then their goal is to maximize what they call, or minimize what they call, the expected inefficiency. And that's kind of the expectation of the utilities that you get under this mechanism minus, or normalized by, the absolute value of the sum of the utilities. So that like sort of what you could, this is the most you could hope for because if people have, in their model, people have different directions of their utilities. And the thing to notice is that the expected inefficiency is basically going to be 0 if everybody votes a constant times their utility. And so you want everybody to vote essentially exactly proportional to their utility in this model where everybody has perfect information. And so then the question is, how do you design a cost function to make them vote proportional to their utility? And this is where the square thing comes out, that each player is trying to maximize their returns minus their cost. And so if you take derivatives, the first order condition becomes that you should say the derivative of the cost function is equal to sort of this marginal utility you get. And if you imagine that the number of voters goes to infinity, your marginal vote essentially like goes towards like the probability of this utility you get becomes independent of your vote, and it becomes kind of a constant as the number of voters get bigger. And so then that intuition says that you have now, in this case, that means this expectation doesn't depend on your VI, and so then this derivative should be a constant, and that's exactly what you want to maximize this or minimize the inefficiency from the previous slide. And what you get is that this thing, the quadratic function, or a constant times a quadratic, has this linear derivative, which is what you want to maximize this inefficiency, or to minimize the inefficiency. Is you need to make this inefficiency 0, you need everybody to vote exactly proportional to their utility. And if you make this simplifying assumption that the marginal probability of changing things, right, becomes constant as n goes to infinity, then the only function that does this is the square. And so this is where they get this, that the square is the only thing that's optimal. And this is why you don't use a cube or a 2.5 power or something. Yeah, and so then there's no inefficiency here. And so their main theorem is basically that in quadratic voting, this expected inefficiency goes to 0 as the number of voters goes to infinity. And so that's when and this is kind of, I think, what sparked a lot of the interest in quadratic voting to begin with, is that they can say in this model that it's the sort of unique optimal. And that was actually something that was really cool, that this was like the only function that does this. Yeah, so if we have time, I can say a little bit about some of these other things about other ways we've looked at voting under imperfect information. So I mentioned earlier that we considered this question of voting like what we call direct voting, where there's some optimal, interest rate, or there's some optimal collateralization ratio, and people don't necessarily know what it is. Everybody gets a signal, which is like the optimal plus some noise. And so I think the optimal is 67%. And the noise comes from distribution. And again, voters have different noise variants. So some voters are much more informed than others. And now I want to cast some vote, which is like my signal plus some prior. And so my choice is basically how much do I weight my signal versus how much do I weight my prior when I cast my vote. And the platform is going to set the parameter to be some weighted average of everybody's votes. So if I vote 65%, you vote 67%, and we both have the taus are each 1/2, it would just take the sum half times each of them. But maybe it's stake weighted, so maybe the tau I is proportional to our stake or something. But the aggregation function is going to be a weighted average, with the weights could be different. And then the payoff everybody gets is basically like how far you are away from the optimal. There's some unknown optimal Q, like the best for the platform would be a 65% collateralization ratio. And imagine like some function that decays as the further you get away from it. And we can actually prove some pretty strong results for a really general class of payoff functions. As long as your payoff essentially gets worse the further you go away, you can prove a lot. And so just like in this case for intuition, you can say, if you just have one voter, they actually shouldn't vote their signal. They should vote their, essentially like their posterior after they get the signal, and they should weight their signal based on what the underlying variance of the true thing is, sort of normalized, like basically how much their in the noise variance is as a relationship to the uncertainty they had, their prior uncertainty. And so this is pretty easy to show, and it actually kind of carries through almost exactly to the N voter case. And you can show that all the voters should essentially weight their signal. They weight it more as their prior uncertainty gets bigger, and then sort of normalized by the uncertainty of all the people. But the interesting thing that happens here is that this tau I is the weighting function of like the stake weighting, or how you aggregate people's votes. And strategic voters will actually shade their signal by dividing by tau I to exactly cancel it out. And so if you have stake weighted voting and people know how informed they are, they're actually going to essentially try to undo that stake weighting. Like strategic voters, if all the voters are strategic, they know that stake weighting is the wrong aggregation mechanism, and they will all shade their votes based on their information, assuming the information is public. And so you do get an optimal outcome from stake weighted voting, but you actually get an optimal outcome from anything because it's the voters undoing your aggregation mechanism, which is kind of a funny thing. And the problem with that becomes is, if not everybody is strategic, if you imagine you have some voters who are truthful, who just kind of vote what they think, then the strategic voters can't undo what the non-strategic voters did, and now the mechanism becomes kind of suboptimal. But you get some really kind of interesting stuff when you try to think about how to aggregate these things. And so this is something that I've been really interested in the past. I'm continuing to think about a lot, because there's so many different voting mechanisms you could imagine, like this kind of continuous voting or this kind of discrete voting. There's the repeated discrete voting. So in Uniswap or in Compound or something, right? There's actually, you can have repeated votes where somebody says, I think the interest rate should be, or I think the BAT collateralization ratio should be 62%. And then somebody comes up the next week and says, I think it should be 61%. And then somebody comes up the next week and says it should be 67%. And you get really interesting dynamics when people are forced to make sequential yes/no votes, as opposed to voting directly. So we've been looking at that a little bit as well. And then we looked at approval voting, where you can vote for more than one thing. So this is like what we were looking at in the case of electing a committee of block producers, the way you elect a committee on like a Cosmos-based chain. But it's also used in MakerDAO executive votes. So in MakerDAO, you can approve of multiple different contracts, and then the one that has the most approvals is the one that's chosen. And that's a really different mechanism than the kind of compound mechanism where we have sequential votes. And you get really different, like these kind of things have been analyzed a decent amount, usually, but almost always in the perfect information setting, where you have people at perfect information. And it's the dynamics get really different when you start to consider kind of them as a crowdsourcing problem. Yeah, that's, are there any other questions? I'm happy to talk more about sort of any of these things.